Welcome. Today, we are diving deep into one of the most powerful and honestly, one of the most intuitive algorithms in all of machine learning, the random forest. We're going to see how we can go from a single, kind of flawed detective to a really robust and wise jury.
I love this quote because it's the foundation for everything we're about to build. A lone detective, that's our single decision tree. They can get fixated on the wrong clues, maybe miss the bigger picture. But a jury, right? A forest of trees. They weigh all the evidence together, and they cancel out each other's individual biases to get to a much more reliable verdict. This is exactly how we fight one of the biggest headaches in machine learning, overfitting.
And this right here, this is the big idea behind our jury. It's called ensemble learning. Instead of putting all our faith in one model, which, hey, might make a mistake, we assemble a whole team. And by combining all of their individual predictions, we end up with a final decision that's way more robust and way more accurate.
Okay, so to really get why a forest is so powerful, we have to start with a single detective on the case, the decision tree. Now don't get me wrong, it's a great algorithm, but it definitely has a few key weaknesses that we need to talk about.
So for our case today, we're going to be tackling a real-world problem using the classic breast cancer dataset from scikit-learn. Our mission? To build a model that can look at a bunch of cellular measurements, things like the tumor's radius, its texture, its perimeter, and then accurately classify that tumor as either malignant, which is cancerous, or benign, which is not. All right, let's get our investigation set up. First things first, we import our tools. We need pandas to handle the data, and then we grab a few things from sklearn for the dataset and our model. Next, we just call load breast cancer to get all our data. Now, to make it really easy to work with, we load it into what's called a pandas data frame. You can just think of it as a super-powered spreadsheet that we can control with code. And finally, we add that target column, which holds the verdict for each tumor, a 0 for malignant and a 1 for benign.
This step is absolutely critical in any machine learning project. We can't just test our detective on the same clues we use to train them. That'd be cheating, right? We have to set aside a part of the data to fairly see how well our model generalizes to brand new, unseen information.
So here's how we split up the evidence. First, we define X as our features. That's all of our data except for that target column. Then, Y is just that target column itself, because that's what we want to predict. Then we use this amazing function, train test split. We give it our X and Y, we say test size equal to 0.2 to hold back 20% of the data for testing, and we use random state equal to 42 just to make sure our split is the same every time we run it. And boom, this gives us 4 pieces, our training data and our unseen data.
And now, the detective hits the books. This .fit method, this is where the learning actually happens. Our decision tree model is just poring over all the training data, looking for patterns. It's figuring out the best questions to ask, like, is the perimeter bigger than X, or is the texture less than Y, to build a kind of flowchart that separates the malignant from the benign tumors.
Let's put our detective to work. First, we initialize the model, basically creating our detective with decision tree classifier. Next, we train it by calling dtModel.fit and handing it our training data. And finally, we use that trained model to make predictions on the test data it's never seen before, with dtModel.predict xtest. We'll store all those predictions in a variable called dtpred.
And hey, the detective's accuracy is pretty good, almost 95%. But here's the big catch I was talking about. A single decision tree is super prone to a major problem in machine learning called overfitting.
This is the perfect way to put it. Our detective has basically just memorized the case file, instead of actually learning general principles about how to solve a case. It gets too caught up in the little details and quirks of the training data, which means it might completely fail when it sees a new case with slightly different evidence. And this is precisely why we need to assemble a jury.
So how do we build this jury? Well, the solution isn't two simple, but honestly brilliant techniques. They both introduce randomness to create a really diverse and wise group of decision makers. They're called bagging and feature randomness. Think of it like this. We're giving each juror a slightly different file of evidence from the main case. Some pieces of evidence might get repeated in their file, others might get left out entirely. This diversity is what's so important. It's the key to getting a final verdict that isn't swayed by one single, maybe even misleading clue.
Now this is the random part of Random Forest, and it's a huge second layer of diversity. So not only does each tree get a different random sample of the data, but at every single decision point, every fork in the road, it's only allowed to look at a random handful of the clues. This stops the whole forest from getting too reliant on one or two really obvious features and forces all the trees to find other predictive patterns. It's genius.
So let's see how this all looks in the code. What's cool is that the implementation is surprisingly simple. We're going to put our jury to work on the exact same case and see how it does compared to our single detective.
Okay, take a look at this. The code looks almost identical to our single tree, right? We import random forest classifier and initialize it. The key difference is this one little parameter, n estimators equals 100. This is where we tell our model, hey, I want you to create a jury of 100 individual decision trees. The rest is exactly the same. We .fit the model on our training data and then .predict on our test data.
And now, the moment of truth. Let's compare the verdict from our lone, maybe a little overeager detective to the one delivered by our wise and diverse jury.
Well, the results are pretty clear. By averaging out the votes of 100 different trees, the random forest gives us a more accurate, more reliable prediction. And it's not just that it got a better score, it actually reduced the number of errors the single tree made. And in a medical context like this, that is incredibly important.
So a really good question to ask when you're building a random forest is, how big should our jury be? How many trees do we actually need? Is more always better?
This chart shows a classic trade-off. See what happens? As we increase the number of trees from 10 to 100, we get a nice little jump in accuracy. But then, when we go from 100 to 200 trees, nothing. The accuracy flatlines. We've basically hit a point of diminishing returns. Adding more trees now would just make it take longer to compute without actually improving the result. Finding this sweet spot is a huge part of tuning a random forest model.
A single tree is pretty easy to understand. You can just follow the flowchart. But a forest of 100 trees, that can feel like a black box. But we can still peek inside the jury room to see what evidence they all found to be the most compelling.
What's really cool is the model can tell us which features, on average, had the biggest impact on the final decisions across all 100 trees. And what we see here is that measurements related to the tumor's worst perimeter and worst concave points were the most critical clues in figuring out if a tumor was malignant or not.
And this right here gets to the very heart of why random forest is so effective. It's all about something called the bias-variance trade-off. A single tree, our detective, has high variance. It's unstable, really sensitive to the training data. If you change the data just a little bit, the tree could look completely different. But by averaging the predictions of 100 diverse trees, the random forest just cancels out all that noise. It dramatically reduces the variance and creates a stable, reliable model that actually generalizes well to new data.
So, at the end of the day, the choice between a single tree and a forest comes down to a trade-off. Do you need a model that's simple and easy to explain, or do you need one that's a bit more complex but way more powerful and robust? What random forest really teaches us is that by combining lots of simple, even flawed models, we can create something that is so much greater than the sum of its parts. And when the stakes are high, well, it's almost always best to trust the wisdom of the jury.
Like and subscribe for Simplify Tech, explaining one concept at a time, simplifying the technology and AI.